M2 Chapter 1 Part 2 Mathematical Induction. In this part, we will discuss how to use mathematical induction to prove some statement. Let's see one of the example. Now, I have one of the statement, n squared minus n plus 41 is prime number, where n is all positive integers. How can I prove this statement is true? Can I use the following method to prove this statement is true? For example, I try to solve it till n is equal to 1. The value is equal to 41. This is a prime number, and n is equal to 2. This statement, the values of n squared minus n plus 41 is equal to 43. It's also prime number. 3, also prime number. Then I can conclude, okay, this statement is true because I try n is equal to 1, 2, 3, or it's also a prime number. Maybe you will say, okay, this is not enough because we have a lot of number. I try all the number up to 40, also a prime number. Then can we say this is this formula must be a prime number where n is all positive integers? I believe that most of you will argue, okay, you need to try all the positive number integer. When I try next, when n is equal to 41, this statement is false. So we cannot use this way. Because sometimes we cannot try all the positive integers. We have infinitely many integers, so that we cannot try one by one. So how can we prove some of the statement, the given statement? Now this video I will introduce one of the argument, which is called mathematical inductions. How can we use this argument? Define the statement first. P of n. P of n is the statement. I try to prove when n is equal to 1, that statement is true. That means P of 1 is true, and I assume sum of the positive k is true. Based on the assumption, that means based on this assumption, I can deduce P of k plus 1 is also true. Then I can conclude P of n is true for all positive integers. Why? Because when I have already proved P of 1 is true. That means what is the relationship between step 3 and step 4? I assume P of k is true. I can deduce P of k plus 1 is true. That means I know P of 1 is true. According to P of 1 is true, I can prove P of 2 is true. Because P of 2 is true, I can prove P of 3 is also true. So that according to this argument, I can prove P of n is true for all positive integers. Because I know 1 is true. When 1 is true, 2 is true. Because 2 is true, we can prove P of 3 is true, and so on. Let's see one of the example. Example 1.5. I want to prove the given formula is true for all positive integer n's. That means I want to prove this formula is true for all positive integer n's. Step 1, remember step 1. Let P n be the statement. 1 squared plus 2 squared plus 3 squared up to n squared is equal to n plus 1 to n plus 1 over 6. Now Pn is the statement. When n is equal to 1, that means what is the statement? 1 squared, what is the meaning of n is equal to 10? 1 square plus 2 square plus 3 square up to n square. If n is equal to 10, that means 1 square plus 2 square plus 3 square plus up to 10 square is equal to 10 times 10 plus 1 times 2 times 10 plus 1 over 6. How about n is equal to 4? That means 1 square plus 2 square plus 3 square plus 4 square is equal to, how about n is equal to 2? That means 1 square plus 2 square. And remember, we end here. It's not 1 square plus 2 square plus 3 square plus up to 2 square. Remember, what is the meaning about the left-hand side when n is equal to 2? That means the first two terms. When n is equal to 1, that means only one of the terms. Okay, this is the step 1. Let the statement. How about step 2? When n is equal to 1, left-hand side, 1 square is equal to 1. How about right-hand side? 1 times 1 plus 1 times 2 times 1 plus 1 over 6. Simplify it, that is equal to 1. It is because left-hand side is equal to right-hand side. So I know P of 1 is true. This is step 2. Prove P of 1 is true. Step 3. Assume P of k is true for some positive integer. Remember, it's sum. That is 1 square plus 2 square plus 3 square up to k square. I assume P of k. That means sum of the values of k is true. I know one of the k's must be true when n is equal to 1. So I have sum of the k's. This formula is true. Remember, I need to use this assumption to prove when n is equal to k plus 1. In general, I will write down right-hand side first because I need to know what I need to prove. K plus 1, k plus 1 plus 1, 2k plus 1 plus 1 over 6. Then the first term is k plus 1, k plus 2, and then 2k plus 3 over 6. This is what we want to prove. How about left-hand side? When n is equal to k plus 1, that means the left-hand side is 1 square plus 2 square plus 3 square plus up to k square and then k plus 1 all square. Remember, don't expand it. Don't expand it. And according to the assumption, remember what we want to prove is that I need to make good use of this assumption to prove when k is true, k plus 1 is also true. So that we need to use our assumption. This first k term is equal to this is by assumption. Do the common denominator times 6. One reminder, don't expand it. I find we have common factor, k plus 1. You can take it out. The first term remains k times 2k plus 1. The second term remains 6 times k plus 1. Simplify. 2k squared plus 7k plus 6. This is equal to k plus 1 times k plus 2 times 2k plus 3 over 6 when you factor. Equal to right-hand side. So that P of k plus 1 is also true. Conclusion. By the principles of mathematical inductions. P of n is true for all positive integer of n. Okay, this is the demonstration. How can we make good use of mathematical induction to prove the statement? Remember, step one, I need to let the statement first, P of n. And then step two, prove when n is equal to 1, this statement is correct. But what is the meaning about n is equal to 1? Very important. What is the meaning about n is equal to 1? That means we have one and only one term in this case. Remember, sometimes we are not only one of the terms, maybe you need to consider several terms. And the left hand side is equal to right hand side. Assume P of k is true. This is your assumption for some positive integers. Make good use of it. Try to make good use of it. The relation, your assumption to prove when n is equal to k plus 1, the left hand side is also equal to right hand side. Okay, next page, example 1.6. Maybe you can pause the video and do it by yourself and check your answer. First two steps. Step 1, let Pn be the statement. Copy down the questions. Step 2, when n is equal to 1. What is the meaning about n is equal to 1? 1 over 1 times 3 plus 1 over 3 times 5, blah, blah, up to 1 over 2n minus 1 times 2n plus 1. When n is equal to 1, 2n minus 1 is equal to 1. Well, this term. And n is equal to 1, this is 3. So, when n is equal to 1, that means the first terms only. Left hand side, right hand side, so which is equal to 1 over 3. So that I can conclude P of 1 is true. Step 3. Assume P of k is true for some positive integers. And copy down the question. Remember, change all the variables from n to k. Step 4. When n is equal to k plus 1, remember in general I write down the right hand side first. Right hand side is equal to when n is equal to k plus 1, substitute n is equal to k plus 1, so this is k plus 1, k plus 1. Simplify, k plus 1 over 2k plus 3. How about left hand side? Copy down the first kth term and then add when n is equal to k plus 1. For the first kth term, I can use the assumption. Remember, this step is very important. And then simplify this denominator and do the common denominator times 2k plus 3 for this term. And then add them together. Simplify, expand, and factorize it. You can cross out the common factor. This is what you want, your right hand side. Remember, draw the conclusion by the principles of mathematical induction. Pn is true for all positive integer n. Try to digest the questions and let's discuss together.